Okay, can everyone see this correctly, or do I need to swap screens? Hang on.
We see presenter view and
Okay,
yeah.
all right. Hang on one sec. I need to reshare. Share this screen. Okay. Too many screens going on here. How's that? Better?
Yeah, it looks better.
Okay.
Yeah, looks good.
Okay. All right. So I think most of you on this crowd here know who I am. But for the purposes of posterity in this recording, I'll introduce myself. My name is Robert Yee. I am currently a senior engineering manager at Cisco, and I actually happen to lead the team, the team of solutions architects responsible for ACI, Nexus 9K, Nexus dashboard, some SAN stuff across the West. So my team handles enterprise customers, commercial select customers, SLED customers, and customers in Canada as well. So it's a pretty wide set of customers that I get to see or hear about. And I thought, it might be a good opportunity for me to touch upon this topic again, right? So I made the one last change to this deck today as I was going through this one more time, right? So I used to do this talk pretty regularly for customers, trying to sell them on the idea of fabric networks and why they should move to fabric networks. And it's been quite a while since I've done this talk. But I realized, the title that I used to have was Fabric Networks or Fabric-Based Networks for Next Generation Data Centers. And I realized that's really not correct anymore. So I'm officially changing it to Fabric Networks for today's data center, right? I think that's a fair assessment based on what I see and I hear now. So when I was a solutions architect, I would go out and talk to customers all the time about ACI and how the underlying technology was VXLAN, and this is what they should be looking at for their next generation data center. And then I stepped away for like 3 years, and then I come back, and then all of a sudden, like all I hear about is, oh, this customer is doing VXLAN, this customer is doing ACI, this customer. So it's like, wow, okay, I wish I could say that I was responsible for all that good fortune, but probably not. But I thought it was timely. So I wanted to reintroduce the topic with you guys. I'll go over a few things. I'll talk about really what the evolving data center network requirements have been. And if you guys have been around for any amount of time, this is probably not going to be new information. I'll talk about what the underlay network is, right, in this new architecture, right? And that's basically based around the spine leaf design and how that kind of solves some things for us, especially with the new requirements. And then we're getting to the overlay. And by default now, that is going to be VXLAN. And then I'll talk about, at least from a Cisco standpoint, what are some of the options for you if you want to deploy VXLAN. And then I'll get into what are some resources, right, if you want to try your hand at practicing on VXLAN, okay? So any questions, any comments before I get started here? Any requests? Okay. All right, here I go. Okay, all right, so goal of the session, right? It's basically, it's not gonna be super deep, super technical. I just wanna entertain you guys for an hour, tell you guys a story, about what's been changing in the data center arena, how these changes or new requirements are being addressed technologically speaking. We'll do a level 1 deep dive into how VXLAN actually works, and then we'll cover again just the deployment options, right? So that's my plan for today or for tonight. And I will start with this slide. So I added this slide in just recently, coming back into the role, talking about where the state of the industry is. And I would love to say that, man, every single customer that I have is deploying ACI, right? That's certainly not the case. But I will say, from the time that I left the role to the time I came back, ACI has definitely picked up quite a bit of steam, okay? However, along the same lines, we have customers that are choosing to go cloud first. And then I'm hearing about customers that talk about hybrid, right? So what does that basically mean, right? So for those traditional customers, what I call the on-prem customers, there's basically two choices as they look at new technology, right? They may just want to go to a refresh of what they used to run, right? And it could have been like Nexus 7K, 5K, 2K. And quite honestly, that's a very old architecture. So even if they go to the 9K, we're talking about refreshing some architectural design as well. And then there are those customers that realize, they are under pressure to make a big shift, to react much quicker, or to react more holistically to network changes, right? Or they can't just make one change and then, the failure starts to cascade. Like they need to make changes kind of all at once. And how do they do that? Like programmatically, right? So that's what I call the big shift. Those are kind of the two customers that I see and hear about. And then there are customers that are cloud first. So their whole thing is, I want to decrease my presence on-prem. I want to build in the cloud first, right? And for those customers, that's a very, I would say, special subset of customers that probably built their application to work in the cloud versus refactoring their application for the most part. Not everyone, but for the most part. But even for those customers, right, they still need a network, even if it's running in the cloud, and ACI could potentially be that option for them. And then there are the hybrid, and I think these are the ones that are having I don't want to say the roughest time right now, but these are the customers that I see or hear about that are really trying to figure things out kind of on their own. And they are, they're having a little bit harder time with things just overall, right? Like, but not just like technically, but trying to decide where does it make sense to run the application, whether in the cloud or on-prem or a combination, and when and where, right? So that's kind of what I see. And it's not that I would say that any one of these are predominant over any other. I kind of see all three of these, right? Probably with on-prem still being the most, and then cloud first, and then hybrid down at the bottom here. That's very roughly speaking the order that I'm seeing it in. Okay, all right. So let's spend a few minutes and talk about what's been happening from a design and requirement standpoint when it comes to data center. All right, so everyone that's on this call probably is aware or familiar with the traditional networking model of a core distribution access type of design, right? This has been around forever. This is the first design that I learned back in the late 90s, and it was even around before that, of course. This is the design that was based on a couple things, right? It was designed based on constraint, okay? So meaning what's the least amount of bandwidth I can put on this network in order to make it work or get by, right? Cost was typically a very important factor on a campus network. Oversubscription is built into the model. If you think about the oversubscription, right? These were networks that were basically designed to work for north-south type of traffic, basically client server. Okay, so the client talks to the server, it downloads a file, and then it works on the file locally. And then when it's done, it saves the changes and it goes back to the server, right? So not a lot of traffic. You can have a lot of oversubscription built in. And then I would say that even today, while this is changing, right? Even on the campus side, this is going to a fabric-based design, like something like SDA. But this isn't really going anywhere, at least not right now, right? It's a very well understood, very mature type of model. And of course, there are other design advantages built into this, right? Troubleshooting and so forth. Okay, so what happened early on when we started having things on-prem called data centers, right? When server rooms turned into data centers, we kind of rejiggered our switches a little bit and maybe added some more buffer in there. Maybe the uplinks were a little bit faster, and those turned into our first generation Catalyst data center based switches, right? Like the Catalyst 4500s and stuff like that, right? But overall, nothing really changed, right? And then come along 2010 and so forth, and moving down the road in terms of years, things really did start to change. Okay, so I would say starting around 2010, a little bit before maybe, we started to see a bifurcation in terms of requirements for the campus versus the data center. And I think that's still happening today, right? So for instance, if you think about your campus requirements, what's happening on the campus, right? What's the biggest driver on your campus networks today? It's not wired ports, not really, right? It's mobility, it's BYOD, right? That's a big thing. And then probably comes voice and video. And then to support that, you need PoE, right? Which became PoE Plus, which became Universal PoE, and I forget what's after that. So in order to run all these things, you need things like QoS. VDI, of course, is very popular now, especially in certain verticals like healthcare. the layer 2 design, layer 2 access design started to shift over to layer 3 access type designs. That's kind of the recommended campus type design now as well. From an access speed perspective, we went from 100 meg to gig to 2.5 gig, right? And then from an uplink perspective, that's gone a little bit faster. I don't know what the latest is, but we have at a minimum 40 uplinks, and I don't know if we've gone to 100 on the Catalyst, but I'm guessing probably yes. Things like SDN are now talked about pretty readily. Exos version is going to be SDA, and the controller for that's going to be DNA Center, and of course things like IoT across the campus. Right, this is what's driving the conversation on the campus. If you shift over to the data center, it's a very different conversation now, right? The data center, again, used to be where you housed your servers, and it was north-south traffic, and it was client server. It was just basically the servers were a repository. That's basically what they did. They maybe crunched some email, but that's about it, right? Moving forward, starting about the 2010s, we started to hear things Hadoop, distributed workloads, high performance compute, all these type of things, right? And those are examples of distributed workloads. And that continues to kind of explode even local on data centers to different degrees.
Hey, Robert. Robert,
Yeah.
can you hear me okay?
I can.
I think you're breaking up pretty bad. I thought it might just be me for a second, but I'm getting
really?
other messages
Okay.
saying that your voice is pretty choppy.
All right, let me try this. I'm gonna try to switch.
Although now it sounds a lot better, actually, of course.
Of course. Okay, let me try to switch over to my home. I may drop for a sec, so if it does, and if it drops this call, I'll restart, okay? So hang on. Okay, can you guys still hear me?
I can hear you okay.
All right, okay, all right. Okay, I'm gonna, and if I start coming in choppy again, just interrupt me. Was I coming in choppy the whole time? Do I need to start from
No,
what?
no, not the whole time, but probably for the majority of this slide is when you started.
Okay, all right, okay, so I'll back up a little bit. I'll back up a little bit then. Okay. All right. So, I was talking about the fact that not really much has changed for a very long period of time in the data center versus the campus, right? But then when you start hitting into the 2010s, requirements really started to differ quite greatly between campus and data center, right? And what it comes down to, and I talked about what's happening on the campus, right? BYOD, voice and video, PoE, right? In the data center, I started talking about things like distributed workloads, virtualization, just ran rampant in the data center, of course, right? We have VMware, containers, microservices. These are all some form of virtualization. The data center hosts now, they don't even connect at 10 gig, 25 gig is, very common now, right? And now that the standards have been set, right? From an uplink perspective, much higher speeds for many, many years now, 40 gig to 100 gig, and now we're talking about 400 gig, right? So all of this is really to support not the north-south traffic, but east-west traffic, layer 2 traffic, okay? We talk about multiple data centers, how do you support things like running multiple data centers across different geographic areas, automation, hybrid cloud, as I mentioned, SDN, and the layer 2 explosion, right? So the traditional model, right, the core distribution access is probably still okay for campus requirements for the most part, although as I mentioned, that is starting to change. But is it really the right model for the data center, right? And that's what we'll be addressing with some of the upcoming slides. So what I'm going to focus on now is really the last point here, right? Layer 2 explosion and what that means in the data center. Okay. Is my voice coming in okay so far?
Sounds good over here.
All right, okay. So let's talk about layer 2, right? Why layer 2 in the data center? For one thing, it's a big part of our virtualization strategy, right? You think about VM mobility, right? That needs layer 2, right? You think about containers, microservices, all that stuff kind of needs layer 2, right? Things like certain protocols just rely on layer 2, right? It just needs layer 2 to work. Layer 2 can be somewhat simple, can be plug and play for the most part. On the rare occasions, you may come into some problems with Layer 2, but typically it's not common, right? And then there are some limitations of layer 2, of course, right? On the access layer, actually at the host layer, I should say, you talk about MAC address tables that don't really scale on the host side or on that first hop network side as well, right? Broadcast domains can become very large and problematic. And if that's the case, then you may see flooding across your network, right? So those are some definite limitations that you need to think about, maybe address in your designs. And then more typical on the network side, we talk about spanning tree, right, to help with issues in layer 2. But spanning tree has its own limitations, right? You talk about spanning tree issues that can ripple across the network. You talk about spanning tree having are limiting bandwidth that's available to you, right? You pay for both links, but you're only really using one. You can load balance using some strategies and so forth, but still you're not getting the full use of your bandwidth. Convergence can be disruptive, even though it's minimal nowadays. And tree topologies, basically spanning tree topologies, can induce paths that are not optimal to good traffic, right? So some things to think about as we talk about data center. Now, what are we doing to address some of these things, right? So this is where I'm going to start talking about things like spine leaf and overlays, right? So I'll start with the underlay network. And what I'm really talking about is going to be that spine leaf architecture, okay? High level, right? We're talking about network fabrics, and architecturally speaking, that's a spine leaf topology, right? You have your spine layer of switches and your leaf layer of switches, right? Internally to the spine leaf architecture, there's going to be some type of routing protocol that's going to tie it together, okay? Could be ISIS, could be OSPF, could be BGP. In some cases it depends. In some cases it's kind of dictated to you. But externally, there's going to be something that kind of ties it all together so it appears or operates kind of as one single element, and that's your underlay versus your overlay, okay? I'm going to go through this part real quick, so I'll talk about it again in a little bit. So where did the idea of spine leaf topologies come from? So this may not be the only two answers, but in the two that I've been researching, this is what I came across, right? There's basically two architectures that have been around for a very long time that kind of blended itself to the idea of a spine leaf, okay? There's the cloth fabric, and then there's the idea of a fat tree, right? So let's get into the cloth fabric. When I first thought about it, I thought, oh, what a weird acronym, right? CLOS. But it turns out it was someone's last name, Charles Kloss. He was a researcher at Bell Labs, and he came up with a highly resilient network to survive. Remember, this is at the height of the Cold War, to survive a nuclear a war in case it happened, right? And it basically consists of 3 layers. There's typically an ingress layer, there's a middle layer, and then there's an egress layer, right? This is in essence itself the topology of the fabric, but each one of these things here itself is a crossbar fabric too, right? So there's a lot of throughput, a lot of resiliency, a lot of redundancy here, right? The other thing is if I took this cloth fabric and I drew a dotted line down the middle and I folded it in half, I basically have a spine leaf network, right? I have a spine layer here, that's my middle layer. And then I have my leaf layer or my ingress and egress layer, right, which is kind of combined together, okay? So something to be aware of, that's kind of where it came from. And then there is the idea of a fat tree, right? And that was more recent, Charles Leeserson of MIT. And if you think about fat trees versus skinny trees, our traditional networks is a skinny tree network, right? Basically, we build in oversubscription as we go up the model, right? Small links, if you think about traditional, uplinks as you go, and the oversubscription, right? This isn't completely representative. Like, let's say this access switch, instead of obviously just 2 hosts, you may have up to 48, right? Up to, 96, maybe even more, depending on the switch, right? So there's a lot of oversubscription built in. However, with a fat tree, you take away the oversubscription you account for the oversubscription by adding more bandwidth as you go up the tree. And that is called a fat tree, right? So as you go up, it gets fatter and fatter, the pipes get fatter and fatter, okay? All right, so this would be a typical representation of what a spine leaf network might have looked like in 2010, right? Maybe for something like a Hadoop network. This is going to be the reference model that I'll be going back to, right? Back and forth. So nothing really to talk about here except the fact that this is a reference I'll be coming back to. Okay, let's talk about actual spine leaf network, right? So typically, not typically, but it is going to be consisted of two elements, right? Or two types of elements, your spine switches and your leaf switches, and they will be connected to each other across layer 3, no exceptions, right? Now, there are some really nice advantages to this type of architecture. It is a relatively flat architecture. It can be super fast and it's very flexible, right? And what I mean by these things is I have any-to-any connectivity. I'm basically one hop away from any other leaf here on this network, right? I can have very high bandwidth. So typically in these data center switches, you may have multiple uplinks configured to your spines, not just a single one. And they're going to be very fat pipes, right? You know, 40 gig, 100 gig, and now 400 gig pipes. Again, very low latency. On these switches nowadays, we're basically talking about cut-through switches, right? Not, you know, store and 4 type switches. And then just, you know, the ASICs themselves are low latency. And then, of course, there's really high resiliency. What I mean by that is, if I needed to add additional capacity, I basically just keep adding more leaves until I run out of ports on my spine switches, right? If I needed to add more overall bandwidth, I, again, just add more spines, right? So there's a lot of flexibility in this architecture. And, you know, it doesn't have to be just these two layers, right? You can build multi-layer, you know, spine leaf architectures, right? As you go up. So it scales very widely. Now, traditionally speaking, right, what would happen if we just deployed this in your data center, right? The spine leaf network that is connected via layer 3. It wouldn't be very flexible and it'd be pretty difficult to manage. And what I mean by that is, let's say, for instance, I have a host. In this case, it's a laptop, right? And as we do, we connect laptops to our data center switches, right? That's a bad joke, by the way. But whatever it is, right? You know, laptop, server, VM, that host is going to have an IP address, right? And if you think about an IP address, it represents two things, okay? It represents identity, okay, first of all. So if you think about DNS, right? DNS basically is identity, right? It's domain naming. It's a simple to understand or use name that maps back to an IP address, right? That's an identity. But it also indicates location, okay? Because this is all layer 3. That means whatever subnets are under leaf 1 are going to be different subnets that are under leaf 2 or leaf 3 or leaf 4, right? And so on and so forth. So this IP address not only represents identity, it also represents location, okay? So now, in a data center, right, if I needed to move, if this was a VM and I needed to move this VM, for instance, right, I would also have to change the IP address. Not very convenient in a data center, right? Because again, in this case, that IP address in this architecture represents identity and location, okay? So these are some of the things that we are trying to address, not just with the underlay, right? The underlay has some advantages, but also some just built-in disadvantages inherently, right? So how do we overcome the disadvantages? And this is where we talk about the overlay network, okay? I'm gonna pause here and just talk a little bit about overlay networks. So if I was to ask you guys, what are some overlay networks or overlay technologies that you guys are familiar with? What would you guys answer with?
GRE.
GRE. What else?
MPLS.
SD access?
TLS. What was that?
SD
Another one.
access?
SD access is in this case is more of the, I don't want to say marketing term, but that's the overall technology. But like actual like overlay protocols, like so we have GRE, we have MPLS, we have, how about IPsec, right? How about PPTP, IP? I don't know what that is, David. You're much smarter than me, but I will believe you on that one. So
IP and IP.
Oh, IP and IP. Okay, but okay, I don't know what that is. But the idea of overlay networks is obviously, you know, it's not new, right? It's been around for a very long time. But the idea of using overlay networks specifically within a data center is relatively new. You know, over the last decade or so, there's been a couple of attempts at it, right? So there was something called TRILL, TRILL, which stood for, or still stands for, transparent transparent redundant interconnection of lots of links. Okay, and I think Brocade, or what used to be Foundry, I think their technology is based off of Trill. Don't quote me on that. Cisco, we used to have something called Fabric Path, which got off to a rough start, just some, you know, like troubleshooting and stuff, but actually worked very well. However, you know, the industry's really kind of standardized on one single technology, and that's what I'm going to get to. You probably know what it is. I'm not going to give it away, but you guys probably know what it is. Okay, so okay, here we go. Right, we're back at this spine leaf network with a layer 3 core. Again, not very flexible in terms of if we wanted to do things like you know, move hosts, right, and so forth. But what if we were able to overlay on top of this layer 3 network a layer 2 overlay, a layer 2 overlay? Okay, Yingyu, you're giving it away, but yes, that is correct. Okay, so if we're able to overlay a layer 2 network, right, basically a VLAN type segment on top of this layer 3 network, we kind of have the best of both worlds, right? So now that IP address represents one thing: identity and identity only, because I can now take this host, I can move it across the network, and that IP address can follow me, because this is still, at least in terms of the network itself, is still one single network segment, right? So that's what that's kind of the holy grail. That's what we're trying to do, right? And there are some attributes that we want to look for in our overlay technology, right, that we want to implement. From a service standpoint, it should be able to service both layer 2 and layer 3. So it needs to be able to switch, and it needs to be able to route. It should be flexible in the sense that you should be able to host it on almost any device, right? You think about IPsec, right? You know, when IPsec first came out, it was available on a PIX firewall, right? That was my experience, at least. But now, then it moved on to routers, it moved on to hosts, and it's kind of ubiquitous, kind of everywhere. You know, same thing with an overlay technology, this layer 2 overlay technology. We want to be able to run it on switches, of course. We want to be able to run on routers if we need to. We want to be able to run it on hosts if we need to, right? And then from a signaling perspective, okay, this is super important. I'll spend a lot more slides talking about it. It needs to emulate what we see today, especially from a control plane learning perspective, right? That is basically default layer 2 type of learning, right? But that can get a little bit out of hand. And what can we do to add a little bit more intelligence to it, right? And that's where the control plane learning comes into play. So service, edge device, and then signaling. Those are like 3 attributes and some of the qualities that we should be looking for, right? So as Yingyu was talking about, the overlay today, of course, you know, I don't think I'm giving anything away if I say it's VXLAN, right? Or virtual extensible LAN. That's what it stands for. All right. As any respectable slide deck will have, I'm going to break down a little bit of the VXLAN frame itself. So, you know, we start with the Ethernet frame, and on top of that, we put this VXLAN header. So the VXLAN, the VXLAN header, the important part is that the VXLAN header itself is 8 bytes. And out of the 8 bytes, we reserve 24 bits for what we call the instance ID, or the VNID, or sometimes the VNI. You'll see it referenced different ways, right? And this is akin to like a VLAN ID, okay? And can anyone tell me how many VLANs there are in any default type of Ethernet network? Anyone? I see
One,
1,000.
isn't it? One?
What is it? What is
One?
it? One? No, it's 4,094 VLANs in any particular, you know, network, right? That's because of the VLAN header itself can accommodate 4,094 VLANs, right? In the number of bits, okay? So, and then there's 4,096 with 2 are reserved, right? So, so this is a very important thing to point out here, right? The VNID, because that's really the key thing here, right? And I'll talk about why that is. Okay, so the VNID, right? It's 24 bits, and if we put 2 to the 24th power, we get something more than 16 million possible network IDs, right? Important point, right? Yep, there you go. Okay, so what does VXLAN really address? End of the day, what does VXLAN do? The first one is VLAN scalability, right? That's the 16 million possible unique of layer 2 segment IDs, right? But really, the more important thing that VXLAN offers, and you kind of have to stitch these two together. They go hand in hand, so I can't really say even more important. I totally take that back. Is the fact that you basically VXLAN basically allows you to route layer 2 traffic across layer 3 networks, right? Layer 2 segment elasticity over layer 3 boundaries, and that is the key, right? So what you do basically is you take a VLAN ID, is one of the 4,094 VLAN IDs, you stitch it to one of 16 million VXLAN IDs, you route that across the network to the other side, and then you unstitch it to potentially, another VLAN ID that can be the same or can be different. But what you're doing basically is taking these two disparate layer 3 subnets and stitching them together using VXLAN. That is essentially what VXLAN is doing, right? As simply as I can describe it. Okay. Okay, so let's come back to this model here, right? So in this case, right, if I'm to illustrate it, what does VXLAN solve for the data center, right? As I mentioned, right, if I was to build out, the spine leaf network, this is what it would look like kind of by default, okay? It's going to be layer 3 connected across the leaves and the spines. And, all the servers or hosts underneath would be kind of limited to their own subnet or set of subnets. And I would have to route in between, right? You can still communicate, you just got to route, right? All right. Now, if I overlay on top of that a VXLAN overlay, my leafs now take on the role of a VTEP, and the VTEP is a software construct. You can have a VTEP almost anywhere. It's just VXLAN tunnel endpoint. You can have multiple VTEPs, right, on a leaf. It's just the construct there. So as I was mentioning, right, now this gives me the opportunity to stitch a VLAN to a VXLAN ID, route that across the network, and then unstitch it, right? So that now allows me to kind of take in this case, I'm illustrating with a single VLAN, but I can now take that VLAN and spread that across my entire network, okay? My entire layer 3 routed network, right? But obviously no one would deploy their network like this. What is probably going to be more common is something like this, right? When I first heard about VXLAN, it was or read about it. It was actually in Network World. I still remember this. It talked about the fact that VXLAN now allows the extension of 16 million plus network segments, and it didn't really talk about the fact that you can route layer 2 traffic. So initially I totally missed the point of VXLAN because I thought, well, what's the use of this? Because my customers, right, in commercial, don't run 4,000 subnets as it is now. They're not going to need 6 million, right? So the article itself didn't talk about the routing part, and I missed it, right? But if you think about a service provider network or a large hosting environment, right? If I went back into this model, okay, this was the traditional model they were running. They would sell you a rack, and this would be it, right? And then, and if you needed to go into another rack, it would be another. It could potentially be another subnet and so forth. And this wasn't very economical for like these large providers, right? These large colo facilities. But now, if you have something like this, it becomes a much more viable business model, right? To run something like this, where you can offer, the extension of a customer's network to any rack anywhere, basically, right? Okay. Make sense so far? All right.
So far, so good.
So far, so good. Okay. All right. So let's talk about that third point that I was talking about, right? How does VXLAN kind of learn? This is a very important part about how VXLAN works. So I'm going to talk about that. So let's start with this model here, right? We have a what I'll call a typical VXLAN network. I have my spine switches, my leaf switches, right? And that's the underlay. And then when I put the VXLAN overlay on top of that, again, my switches take on the role of a VTEP, right? And then there's the VXLAN encapsulation. So how do these hosts, find each other, right? Let's do a walkthrough of that. Okay. From a flood and learn perspective, this is VXLAN by default. This is how VXLAN would work for any vendor, or should work for any vendor, right? Let's say, I have 3 VTEPs here, 1, 2, and 3, and they each have their own tables. In this case, VTEP 1 sees MAC address A on VNI 30,000 on interface E112, right? And then same thing for, the other VTEPs as well, right? It sees their own respective hosts and so forth, okay? So what happens, let's say, if host A needs to talk to host B, right? In a regular Ethernet network, host A would send out a broadcast and ARP for host B. Well, that's not going to change here either, right? That's going to host A is going to package up an ARP request and send it out across the network and say, hey, who's got MAC address for this IP address, right? So what will happen is that request is going to get intercepted by VTEP 1. VTEP 1 will then package up that request, forward it on across a multicast address on VNID 30,000. That will then end up on VTEPs 2 and 3. VTEPs 2 and 3 will then add another entry to their table for MAC address A, because it's seeing this, right? And then it forwards that broadcast along and says, hey, does anyone on my local network have the MAC address for IPB, right? In this case here, VTEP 3 says no, but VTEP 2 says, oh yes, I have, or the host here, host B, oh, that's me, right? So it's going to reply back. VTEP 1 now then adds that entry into its table here, right? So now VTEP 1 is aware of where MAC A is locally, and MAC B is across the network to the IP address for VTEP 2, right? That is, in a nutshell, outside of the VXLAN part, that is flood and learn. That is regular Ethernet, right? It's just here encapsulated within the mechanisms of VXLAN, okay? And then from a forwarding perspective, okay, so now if host A needs to actually forward a unicast traffic to host B, it's going to forward that onto the VTEP. The VTEP says, oh yeah, I know MAC B. It's on VNID 30,000 at VTEP 2. Okay, forwards the traffic onto VTEP 2. VTEP 2 takes it, says, okay, I have MAC B. I will then forward it on to port E14. Right, pretty straightforward. Again, on the two ends here, that's basically just Ethernet. In the middle, that's kind of the VXLAN part, okay? All right. That is how flood and learn works within a VXLAN environment, and that is VXLAN by default. Now, moving forward a little bit, when I originally created this slide deck, this was not the standard yet. This was kind of the emerging standard, but there is a control plane for VXLAN, and that is MPBGP EVPN, or I think nowadays kind of referred to as VXLAN EVPN. So it's basically multi-protocol BGP with some extensions added in to allow for address sharing, or how to find your hosts in a VXLAN network, right? Okay. What are some of the things that it does, right? So it does host route distribution decoupled from the underlay. So the underlay has its own routing protocol. It's going to do its own thing. This is all up on the overlay, right? It uses basically a form of BGP, and it uses basically route reflectors. So if you guys are familiar with BGP, this is all going to sound very familiar to you guys, right? So let's go over this model here. Okay, so in this case, right, from a protocol linking perspective with a control plane, let's say host A connects to VTEP1. VTEP1 sees it, and the same thing for VTEP2 and VTEP3. It sees its respective hosts. It's going to take that information, and it's going to forward it on to the local route reflectors, okay? And the route reflectors are typically configured on the spines. And then the spines will then reflect that back to everyone else. So then on the VTEPs are now aware of all the different hosts across the network, okay? Pretty straightforward in that sense. Is there a question? Okay. So here's a practical example, right? Let's say in this case here, a host attaches to VTEP1. VTEP1 sees that the host attaches. It will send an advertisement to the route reflectors, and then the route reflectors will then take that information, send it back out to the other VTEPs that it's aware of, right? So a couple of bits of information that's included. It's going to be a choice of next hop, what the encapsulation is, and then also a sequence number, okay? And that sequence number is important in case this host decides to move locations, right? Like in case of a VM moving, right? So let's say the VM does move. It goes from VTEP1 to VTEP3. Well, now VTEP3 is going to see, oh, wait a minute, I now have host A. I'm going to send an update to the route reflectors. The route reflectors then send that out to the other respective VTEPs. And then it updates basically the same information saying, I'm now the next hop, right, V3, and I'm going to give it a sequence of 1, right? So it's going to increment it by 1. So you know that's going to be the latest, and that's the one that you should flush out the table entry from the previous and go with this one, right? Okay. And then there's an element of a convenience or ARP suppression, right? This is kind of a nice thing to have. So let's say in this case, we're back to the model where the VTEPs are aware of where all the different hosts are on the network. So let's say now host A needs to talk to host B, and it does an ARP. So that ARP is then intercepted by VTEP1. Okay, VTEP1 says, whoa, wait a minute. I actually know where host B is. There's no need for me to send out a multicast or emulate a broadcast. I can just tell you where to find it, right? So then it replies back to host A, and then host A will then just go ahead and forward that on, right? Oops, sorry. Forward that on. Okay, so that's if it knows about where host B is. So now what if there is a miss, right? What if it doesn't know where host B is? Well, let's talk about that, right? So kind of same thing happens. Host A is going to package up an ARP, and VTEP1 takes a look at it and says, okay, I actually don't have that in my table. I'm going to go ahead and flood that out, right? Just like before. I'm going to go ahead and flood it out. And then just like I went through before, it's going to go through the same process, right? Of flooding it out. And then in this case, host B will reply back. But something a little bit different happens with a control plane, with an EVPN control plane. When VTEP2 sees the reply back, it will do two things, right? It's going to update the route reflector, and then the route reflector will then update all of the respective tables, okay? And then it'll forward that unicast back to VTEP1, which then gets forwarded back to host A. So in this case, again, it is kind of the best of both worlds, right? If it knows about it, it's just going to intercept it locally and forward it on so it suppresses the ARP. But if it doesn't know about it, it can always fall back to flood and learn, okay? Okay, so I have a slide on how it bridges traffic. Basically, checks the table. It knows where it is. In this case, it's MACB, IPB, VNID 30,000, same VNID, and knows, okay, that's located across the network here at VTEP2 and forwards it on, right? Now, from a routing perspective, it is a little bit different. So let's say in this case, host A wants to talk to host F, okay? It'll take that, it'll forward it onto the gateway, which again is the VTEP. The VTEP says, okay, wait a minute. I know where this is, right? It's MAC-F, IPF, but it's a different VNID. It's 30,005. So I'm going to repackage it with a new VNID of 30,005, and then I'm going to send it to the IP address of VTEP2, right? And that gets forwarded on. VTEP2 then unencapsulates it, sends it to host F. Okay, so that's how basically VXLAN is going to route. Right. So as I mentioned, right, that's kind of the third part, right? The layer 2 as well as the layer 3. And in VXLAN, you can have two types of gateways, right? You can have a traditional centralized type of gateway. You can use even things like HSRP or whatnot, and that would work. But there's a more efficient way to do it, and that's with a distributed anycast gateway, and that does require a VXLAN EVPN control plane, right? So let's see here. Let me build this out. So, okay, so if we package everything together, right, what does VXLAN now solve for the data center, right? So I left off at this slide, and then now if I add the control plane, the route reflector, okay, whenever the VTEP sees an update from a new host being added to the network, it'll send it to the route reflectors. The route reflectors will then send it back out to the different VTEPs to populate their respective tables. And then on top of that, with the control plane, you're able to run that distributed anycast gateway. So the difference between, an anycast gateway and something like HSRP is the fact that that gateway, that default gateway, can live on every single one of these top of rack switches. Okay, and whatever that server is, it's just going to use the most convenient gateway that's local to itself, right? So definitely another convenience there, right? So if I break it down, there are definitely some nice advantages of VXLAN. The fact that it's routing layer 2 traffic means that you can take advantage of equal cost multipathing. You can basically send any workload anywhere, right? It's a very flat network. I have any-to-any connectivity between the different leaves. Allows for things like seamless VM mobility across a very wide network. The scale up to 16 million segments. I will put a caveat on that because, of course, that's kind of limited to what's on either end of that, right? But it's definitely possible, right? Multi-tenancy with traffic and address isolation, meaning, and something I didn't really cover, is the fact that VXLAN itself is an isolation technology, but it also works with things like VRF as well, right? Integration of physical and virtual. I talked about the fact you can run it on switches, you can run it on servers, you can run it kind of or multi-tenancy. Thank you, Jason. Standards-based now, although I would say interoperability is kind of on your own, so to speak, right? Like we'll support our portion of it, another vendor will support their portion of it, so you might be a little bit on your own there. And then of course the VXLAN EVPN control plane. Okay, so we're almost at the top of the hour. I don't have too many more slides, but I'll pause here and ask if there are any questions. If not, I'll keep driving here. All right.
Yeah, press forward.
Press forward. All right. So we're almost done here. So if you wanted to deploy VXLAN today on Cisco equipment, what are your options? How would you go about deploying it, right? There's a couple things here, right? So the first one is going to be CLI. You can simply just deploy VXLAN using CLI. Totally doable. It's a lot of work though, right? If you guys have ever deployed VRFs, it's like VRFs and then there's VXLAN. So there's like double the work, and then you got to take that and kind of multiply that across the X number of switches that you're managing, right? So this might work, for certain environments, especially if you're using a switch that has some automation capabilities, right? Could work, right? Could totally work. So this is an option for you. There is also something called DCNM, or Data Center Networking Manager. And this is the most recent version. Originally, this tool came from the SAN world. And then it was kind of repackaged to work with Nexus switches as well as our SAN switches. And we've kind of continued down that track. So for SAN, it's kind of a slightly different tool now, but we still have DCNM for networks, right? And DCNM is going to be basically a GUI-based version of what you're able to deploy via CLI with some conveniences built in, right? Some really nice conveniences built in. So that's DCNM. I'm not going to get into the details of it, but that is available to you. And if you were going to deploy just VXLAN, I would definitely recommend DCNM over CLI. Okay. Now, there's also ACI, or application-centric infrastructure. And this is kind of a fully packaged version of VXLAN, and in fact they call it IVXLAN on the underlay. You will never touch the VXLAN portion of it. The deployment is relatively simple itself. There's a very detailed GUI to manage ACI, but really in reality, ACI is not best managed via this GUI here. It's best managed via the API, right? So this is where we start talking about programmability. We talk about consuming the network versus configuring the network, right? And in certain instances, ACI can make a lot of sense, okay? I'll give you an example, right? Right as I was transitioning out of my role, I was talking to a customer in Southern California, and they had multiple data centers, 14 data centers, and they were using a mix of Catalyst and Nexus switches, and all their networks kind of grew organically. And this company is the 800-pound gorilla in their field. And they had certain SLAs with their customers, but whenever they made a configuration change, whenever they added a customer to the network, it cascaded all sorts of problems down the road because they needed front-end connectivity for customers, for their customers. They needed back-end connectivity for their customers and for admin. It just caused all sorts of problems. And plus the fact that 14 data centers, multiple customers, in that case, like ACI was going to be a no-brainer for them, right? And they've been pretty successful with ACI. And then, so those are kind of the three options, right? Like CLI, DCNM, and ACI, right? And there may be some other corner cases, but generally speaking, those are the options for deployment. But once you have it deployed, like how are you going to manage things, right? DCNM has a certain amount of nice management and visibility built in, but so does ACI, right? The ACI GUI itself. But there's also something called Nexus Dashboard, and Nexus Dashboard is really built around day 2 operations. Nexus Dashboard is a physical cluster today, and down the road it will be in the cloud. But it's basically a physical hardware platform today. It's a highly resilient cluster of servers that is a hosting platform that offers a single pool of storage, right? A data lake, if you will, to run applications on. Okay, and the applications today is going to be like Nexus Dashboard Orchestrator. And what Orchestrator does is it allows you to orchestrate deployment, configuration for multiple data centers and across different types of technologies like ACI, as well as just VXLAN itself. Nexus Dashboard Insights. This is actually similar to DNA Center Insights, right, or Assurance, right, where a lot of insights or intelligence is built in to the tool itself. They call it like having a CCIE in a box. In a lot of ways it is, right? A lot of the technology is built upon years and years of TAC experience, right? So it can tell you when it's anticipating a failure to happen. It can tell you when your configuration is incorrect, and it can tell you how to fix it, right? And I think we had a Nexus Dashboard presentation about 2 months ago, if I remember correctly. There's Nexus Dashboard Data Broker, which used to be just Nexus Data Broker, which is taking your Nexus switch and turning it into I can't think of the word right now, where you can divvy up the traffic and send it to different devices, right, for the purpose of analytics. And then it's also a platform for third-party applications, and those will be coming online shortly. So that's kind of Nexus Dashboard, right? And that's kind of our day 2 ops strategy here at Cisco. And if you're going to be deploying, ACI, VXLAN, anything like that, it's probably something you want to think about. As I mentioned, today it's a physical cluster. I believe very soon it'll be virtualized or available to be virtualized, and then down the road will be as a service. So that wraps up kind of the talk track that I had for tonight. The last thing I'll leave you with is some resources if you want to go and try out some VXLAN for yourself, right? So Cisco has something called dCloud, which is our demo cloud. And in dCloud, we have a lot of different demos that you as Cisco customers have access to if you wanted to learn how to do something, right? But also in there is a sandbox, right? And it's basically just virtual routers, virtual switches that you can bring up and run whatever configuration you want to run on. There is a virtual instance of a Nexus 9K on there that you can actually run VXLAN on, right? So you can set up your network how you like, and then you can take a VXLAN config guide or configuration example and just test it out, right? And run that for just a simple idea of what VXLAN can offer you. Okay, I think I'm just 2 minutes over, so I will stop there and stop sharing. And any comments, any questions? Got to put you all to sleep.
It was a good talk as always, Robert.
Thanks, Jason.
No, not sleeping. It was a good one.
So yeah, I guess the last thing I'll just say is a VXLAN's been around for a while. There's when I first started talking about it, it was definitely like a new idea with customers, and they were not going to be deploying this new technology. Now today it is much more widely adopted. Almost every conversation that we have with customers, they're bringing up VXLAN with us to talk about, right? Like, can you tell me about VXLAN? Right, so definitely a big shift in what I'm seeing and hearing out in the field with you guys. So something for you guys to think about. And with that, I will stop the recording.